So we just looked at how to solve this system using matrices, um, first using the inverse matrix. Now let's look at how to solve it using Cramer's rule. And this is section 10.6.2. Now recall that the solution can be determined by taking the inverse matrix and multiplying it by the right-hand side, C. And this is true if A is square and its determinant is not equal to 0. Remember, if the determinant is equal to 0, then A is singular and it is not invertible. But this is true if the determinant is not equal to 0. And we can write that out. We can describe the ith component of this, or the ith element of the solution, writing out this matrix multiplication. If we sum over the jth column of the ijth element of the inverse matrix times each element of C. So this is, I'm just writing out this multiplication using the summation, and then writing out each term of the inverse matrix. Again, we have the adjoint matrix, which is made up of the jith cofactors divided by the determinant of A, again times each element of C. Now, if you look at the second expression, the numerator of the second expression is a lot like the determinant of A. And just to remind you what the determinant of A looks like, if we sum over J, we again have the cofactor of the jith element times the jith element of A with I fixed in this sum. So I is just, it's fixed at a fixed value and we're summing over J. So the numerator looks a lot like this, except for, let's see, except with column I of A, so AJI is column I of A, replaced with the C vector, with CJ. So therefore, thus, a quick way to compute xi is to take the determinant of A, but with column I replaced with C. And this is called Cramer's rule. And this is after Gabriel Cramer, uh, 1704 to 1752. So let's look at an example. So here we have a system AX is equal to C, and A is 1, 3, 0, minus 2, 3, 1, and then 0, 1, 1. And of course, X is X1, X2, X3, and C in this case will be 5, 1, and minus 2. So we need to take the determinant of A, and if we do that, we find that the determinant of A is equal to 8. So to solve for x1, here I is equal to 1, we take the determinant of this matrix, but with the first column replaced by C. So the first column is 5, 1, minus 2, and then the rest of the matrix is unchanged. And we take the determinant of that. So we've inserted in the first column the C matrix, and then we divide, we need to divide that by A. And let me make sure I have that. And okay, I forgot to write that. We have to divide by the determinant of A. That's what completes Cramer's rule. A quick way to compute x sub I is to take the determinant of A, but with the column I replaced by C, divided by the determinant of A. Okay. And so going back to our example, when we do that, we find that x sub 1 is equal to 1/8. X sub 2 is again the determinant of A, but this time with the second column replaced by C. So the first column is unchanged. It's the second column that's replaced by C, and the third column is unchanged. And again, the vertical bars again represent the determinant, and then we got to divide by the determinant of A, and this is equal to 13/8. And finally, x sub 3 is the determinant of the A matrix with the third column replaced by C, the C vector on the right-hand side. And that gives, and of course we have to divide by the determinant. And this gives minus 29/8. And so we have our solution by just applying Cramer's rule. We have our three values of x by taking these three determinants. And just so you know, there's a MATLAB function called the determinant, which will save you some time. In applying this method to solving this system of equations. So that was Cramer's rule.